All right, this is part 3 to the concepts, section 4.2, 4.3. And so I'm going to go more in depth, I guess, or explain what a definite integral is. The last video we talked about finding a Riemann sum, and we did it based off 4 rectangles of equal width. And we got the approximate area being 3.75, and that was using the right endpoints. And that's using our recurring example, f of x equals x squared on 0 to 2. All right, so that was using 4 rectangles. Now what happens when we use n amount of rectangles? So recall that the Riemann sum is provided by this, the sum of f of ci times delta x, where delta x is the width of the rectangles, and it's given by b minus a over n. And then in a general formula for the right endpoints, ci is equal to a plus I times delta x. So that way, if you use the general formula for the right endpoints for ci, you don't actually have to write down all 4 subintervals and then plug each right endpoint of each subinterval into the function. You can just get it as one sort of general value. So our example was x squared, and we had 0 to 2 as our interval. Now, if we used n rectangles, whereas before we had 4 rectangles, before it was 2 minus 0 divided by 4, which gave us a half. But in this case, it's 2 minus 0 divided by n. So we have 2 over n as our width, and that's for each rectangle, and there's n of them. So I plugged this delta x value, 2 over n, into the formula for the right endpoints, so I can find what is the right endpoint formula. All right, so plugging it in, you get, so a is 0, because that's what the a value is 0 and b is 2. So it would be 0 plus I times delta x, I times 2 over n. And so our ci values is just 2 over n times I. Then I want the heights of the rectangles, so I plug those into x squared. So that's what's going on here. F of ci is equal to 2n times I squared. Well, that's going to give 4 squared over n squared times I squared. So the heights of the rectangles I circled in green, and then the widths are all 2 over n. So I plugged those values into the formula for Riemann sum, just like I was doing in the previous video. It's just now we have n that we're dealing with. So plugging it in, so we have our f of ci is the 4 over n squared times I squared, and then the delta x value is 2 over n. So then it comes a matter of simplifying this. Well, then I could do 4 times 2 is 8. N squared times n is n cubed, so that gives me 8 over n cubed, and then times I squared. And I basically want to keep anything, or just keep the sum only consisting of I. So the 8 over n cubed, I can factor that out of the sum, so that I just have the sum of I squared. Then from the previous video, we talked about summation formula, and the summation formula for I squared was n times n plus 1 times 2n plus 1 over 6. So I plug what that is, the stuff in orange into the Riemann sum. So then you have 8 over n cubed times the same stuff in orange, and then I try to reduce this. Well, I can cancel out n from n cubed to make it n squared in the denominator. And then 8 over 6 can be reduced to 4/3. So using n rectangles, provided that we use the right endpoints, we get the Riemann sum to be this: 4 times n plus 1 times 2n plus 1 over 3n squared. All right, that's the general formula you can use. Apply it to any amount of rectangles you want. Just for sake of demonstration, let's say I did 5 rectangles. So we already did 4. So you just plug 5 in for n. So for 5 rectangles equal width using the right endpoints, you get the Riemann sum to be 4 times 5 plus 1 times 2 times 5 plus 1. All of that's divided by 3 times 5 squared. All right, so that's going to be equal to 4 times and then 5 plus 1, so that's 6, and then times, and then 2 times 5 is 10, plus 1, that's 11. Divided by 3 times 5 squared, well, 5 squared is 25, so I have 3 times 25, which is 75. All right, so the point is that you can use that for any amount of rectangles, plug in whatever value you want for n, and that will give you the sum. So if I were to calculate 4 times 6 times 11, I'm just going to leave that up to you to do, divided by 75, that's going to be the Riemann sum used for 5 rectangles. Now, again, this is the general formula for any n amount of rectangles. So if we take the limit as n goes to infinity, that means we're going to get the exact area. So I said in the previous video, if you sum infinite amount of rectangles, that's going to give you the exact area. So that's the same thing as taking the limit as n goes to infinity. So to take the limit, so I just pretty much wrote the same stuff over again, but in green, I put lim n to infinity. And so I just focus on the right-hand side. So I pretty much just FOIL everything out or distribute everything out on the numerator. And you get n squared, or 8n squared plus 12n plus 4 up top, and then 3n squared on the bottom. Now, from previous section 3.5, we dealt with infinite limits. And dealing with infinite limits of a rational function where you have a polynomial divided by a polynomial, you focus on the leading terms. So we have 8n squared and 3n squared, top and bottom. Those are the leading terms. So since we have the same exponents for the leading terms, then the infinite limit is going to be the ratio of the coefficients of the leading terms. So the limit as n goes to infinity, just we focus on the leading terms, and then the leading terms is 8/3. The leading coefficients of the leading terms. All right, and that gives you 8/3. And 8/3 is the exact area for f of x equals x squared on the interval 0 to 2. So pretty much this. We found the purple region, that area is 8/3. And that was doing that limit, an infinite limit as n goes to infinity of that Riemann sum, where we're using n amount of rectangles. And then I wrote here, recall from section 3.5, where we dealt with infinite limits, and I focus on the leading terms, top and bottom, like ax to the m divided by bx to the n. And you just see, well, is the top exponent smaller than the bottom exponent? And if it is, then you have 0 is the infinite limit. It means the same thing as a horizontal asymptote is y equals 0. Now, if the exponents have the same, or the same, then it's the coefficients of the leading terms, a divided by b. Same thing as having it being a horizontal asymptote with a divided by b. All right, so all of that, again, we talked about finding a sum approximating the area of x squared on 0 to 2, and I showed 2 rectangles what that area was, and you could use the right endpoints or left endpoints. And then I tried 4 rectangles. Now here I just tried n amount of rectangles, and this was the general formula you get for n amount of rectangles. And then if you apply the limit as n goes to infinity, that's going to give you the exact area, which is 8/3. All right, and so finding this infinite limit of Riemann sums will work for finding the area of any continuous function, provided that the function rests above the x-axis. So in our example, we had x squared. The green curve is lying above the x-axis. So the purple region represents the area that's under that green curve, that's bounded from the x-axis to the curve. But you can also use this limit, infinite limit of Riemann sums, to find the value you would get if the function rests below the x-axis. Now, if the function just doesn't rest above the x-axis, you would just get a negative value. And since it's negative, that wouldn't represent area. In our case, it rests above the x-axis, so it did represent area. All right, so that infinite limit of the Riemann sum is actually called a definite integral. And so this is the definition of a definite integral. So given the Riemann sum, the definite integral written as, and you've seen this integral sign before, and then so it's basically looks like the indefinite integral with section 4.1. It's just now you have a and b attached to the top and bottom of that integral sign. So we had indefinite integral was 4.1. So that was indefinite integral. And you had antiderivative rules to find that. But here, this is a definite integral. And the difference is that it has the values a and b, top and bottom, on the integral sign. But this definite integral is equivalent to taking the limit of the Riemann sum as n goes to infinity. So this is pretty much the main point of section 4.2 and 4.3 is that you get the definite integral equaling this infinite limit of a Riemann sum. Now, if f of x is continuous, and so f of x has to be continuous for this to be applicable. And then also delta x we talked about was the width, and that is found by doing b minus a divided by n. And n can be thought of as how many rectangles you want, or it could also be thought of as how many subintervals you want. And then the CI part, like I mentioned earlier, that's any value you choose in each ith subinterval. And then I normally just go with the right endpoints. So that's found by doing a plus I times delta x. So note if the definite integral represents the definite integral represents area if the function lies above the x-axis. But this doesn't have to be a positive value. It really depends on the example. So for a recurring example, the definite integral of f of x equals x squared on 0 to 2 is the following. So I have the integral sign, and then our function x squared, and then I used 0 and 2. That's the same as our a and b of the interval. But that's equivalent to this infinite limit, which we already found this earlier. All right, that's what all of this was doing here. And we already found all that. We took the limit and we got it to be 8/3. So the definite integral is equal to 8/3. In this case, our function x squared rests above the x-axis on 0 to 2. So this 8/3 value would in fact represent area. All right, so that's pretty much the main points. I will go into actual examples in the following videos. I just feel like I would cover the concepts, and it took me about 3 parts to do this for the concepts. But basically the main idea is you started out discussing how you can find an area under a curve or approximate it using rectangles. And the more rectangles you use, the better the approximation. And so a general formula for that sum of n amount of rectangles, I use n for just an arbitrary value of rectangles, that sum is called a Riemann sum. All right, so we have the Riemann sum. All right, and then we had our delta x was the width. The f of ci thing, that was the height of the rectangles. And this gives you the sum for n amount of rectangles. So that gives an approximation for the area. And that's provided that the function is positive. All right, otherwise it wouldn't be an area, it's just be a negative number. So now if you take the limit of that, that gives you the exact area. And again, that's if f of x is positive. And then this itself is just called a definite integral. And it's just written as the integral sign from a to b of f of x dx. So it's equivalent to that limit. And again, it represents area if f of x is positive. But you can also find this value without it being f of x being positive. But the indefinite integral can be negative. In which case that wouldn't be an area. We don't know what it means to have a negative area. So it can be negative, which means it wouldn't represent area. It would just be like a negative number you get. All right, so that's summarizing all of the main points for these 2 sections. And next video, I will, well, at least the main points there. I went into other details about like what the CIs are and all that stuff, but the next videos go into examples. And the type of examples, well, we'll find approximate area. Using right endpoints, left endpoints. Finding the Riemann sum. And then finding that limit. So finding the definite integral. All right, that's what's going to be in the following videos.